Moving on to 3.2, titled Basic Concepts of Vector Spaces. So just more stuff on vector spaces, moving on to kind of mimic what we've done in the previous sections and chapters using just Rn concepts. And now we're in the more general idea of a vector space. So first, guess what? We're going to look at subspaces. So very similar, it'll be defined very similar, but just kind of more of the general statements of how we do things. So subspaces, this is definition 3.4. So let's suppose and let V be a vector space. And W a subset of V. So then we want to define when W is a subspace. So W is a subspace if W is closed under vector addition and scalar multiplication. So if W is closed under vector addition and scalar multiplication. So let's take a look. And I mean, basically, we also have in there that it fulfills all the requirements. So, fulfills all vector space requirements. So, though the idea is, though, if V, this is the next theorem, they kind of go together. So this isn't really, this theorem is really all you got to show. So theorem 3.2 has to do with just showing closure of both of those. And so this statement is in there as well, but really it's just the next two things. So this piece is part of that 3.4. So in 3.4, let me read it to you. A subspace W of vector space V is a subset W of a vector space V is a subspace. That's what we're actually defining. Let me highlight that. Where addition and scalar multiplication of vectors W produce the same vectors as their operations in V. So it's what you'd expect. And as I wrote up here, the theorem is really just specifically stating all you got to show is closure. All right, so this is the test titled Test for Subspaces. So then let V be a vector space and W will be a subset of V. W is a subspace if and only if A, 0 is in W. They don't say that in theirs, but basically that's something you can test. So that's like an easy test. If 0 is not in there, then you're done. It's sort of a separate one that I throw in there from a more advanced book actually. because if it's true for scalar multiplication, R could be 0, and then it has to be in there. But that's a way to eliminate something real quick. Okay, then if U and V are in W, then their sum, of course, is in W. So that's closure under addition, right? Okay, and then ABC, if U is in W and C is real, then C times U is also in W, element of. So again, that's closure. Oops. So really, to show something's a subspace, you really just need to do these two things, and you only need to show closure. So sometimes I write that down. Only need to show closure for subspaces. Because all the elements W are already in V, so then all those other operations have to hold if V itself is a vector space. You want to just show that it's always contained in that same subset. All right, so let's look at some examples now. Oh, and then just again, this one is usually used. You don't have to show that because C takes care of this being in W. But this is again, I already said this. This is an easy way to show that something is not a subspace. So if the 0 element is not in W, you're done. It cannot be a subspace. So let's do this example. All right, so an n by n matrix, so like a square matrix, M is a diagonal matrix, or called a diagonal matrix, if basically all the elements except the diagonal are zeros. So the way you can write that is this: if M, the entry M sub ij, is equal to 0 whenever I does not equal j. So think about what that would mean. So to show this, we have two diagonal matrices. So if A and B are diagonal matrices, then whenever I does not equal j, we have A plus B sub ij equal to A sub ij plus B sub ij equal to 0. And then we have, of course, C times A sub ij equal to C times ij. This isn't going to change, just multiplying every component, right? So this shows that everything's 0 if they're not the same. Okay, so that tends to work out. Let's do let me give you just an example. So you can, this is just for your benefit to look at. So if you have A, and this is like a generic example, and I chose to do a 3x3. So A11, 0, 0, 0, A22, 0, 0, 0, A33. So that's what a diagonal matrix looks like. And then B needs to be the same size matrix. B11, 0, 0, 0, B22, 0, 0, 0, B33. So then think about it. If you add those two together, you're going to be adding those components, and you end up with Aij along the diagonal. Everything else still remains 0. So this plus this is 0. This plus this is 0. Okay, so if you can picture that as a sum, then you're good. I mean, it remains, when you add diagonal matrix, they remain a diagonal matrix. And then scalar multiple, C times A, you're just going to multiply that diagonal by C. Everything else zeroes out. Okay, so that's what this shows, is when they're not equal, but it's just kind of hard to see. So then, well, that's it. So both hold, therefore make your conclusion. Therefore, the set of diagonal matrix matrices, I should probably say, the set of diagonal matrices is a subspace of V of square matrices. Well, I guess it would be for any matrix that's a vector space. Okay, next example for subspaces. We can go on and on and on for subspace techniques. Guaranteed question, you're going to get one of these where you're going to show it's a subspace or not, and then you got to show a counterexample if it's not a subspace, or show that closure works, etc. It's pretty straight up stuff. All right, so let's do another one about this set. So think about this one. So consider the set of matrices that are M by N having non-negative entries. So all the entries are non-negative. So it could be 0, but then everything else. So it has to be 0 in there, right? You need the 0 matrix, but other than that, they're just non-negative. Is that a subspace? So you can check it by just thinking about it, right? You can do like A, B, C, D, E, F, G, H. If you add matrices together like that, what's happening? So this would be your research. So in your research, if you did this, you add positive numbers, they stay positive. Okay, that's all cool. Okay, so the closure for addition works. 0 is in there, so you're good there. What about scalar multiplication? Okay, so if you had R times a matrix, A, B, C, D, and R can be anything, the answer is no, of course. Okay, so this is not closed because R is in the reals, right? R could be in the reals, so R could be less than 0. Then when you get R times something positive, it becomes negative, therefore not closed. Okay, so scalar multiplication. Okay. Let's see what else we have. Next one, let's do an example. Let's talk about some polynomials. All right, so let's let n be 0, 1, 2. Okay, then the set of polynomials. So then P sub n, we'll say, is the set of all polynomials where n is non-negative integers. So then earlier I defined P sub n less than or equal to 2. So this is basically all polynomials. It's actually infinite too, because I put dot, dot, dot. So this is, if n is 0, you get just constants. So those are the real numbers. If n is 1, you get linear. You get linear cases. If n is 2, you get quadratics, etc., and it keeps on going forever. So that's all polynomials. All right, so what about the set of polynomials where n is less than or equal to 2? So we already showed that's a vector space. So is this a vector space? I mean, is that a subspace? This is clearly a subset. So clearly we have that that's a subset of P sub n as n is defined here. But is that a, do we have closure? And we already kind of showed that, right? Yes, we have closure. So you'd want to be able to show this stuff for closure. So you want to be able to do these polynomials and show that you add two polynomials and it stays in the set. Okay, and that stays in polynomials of degree 0, 1, or 2. And then 2, you want to be able to show that a scalar multiple stays in the set. So you can be more careful about that by choosing a polynomial of a2x squared plus, I don't want to use that. Try that again. So you can do that by choosing two polynomials like this and then showing each case. A2x squared, a1x plus a naught, and then you can choose your q to be similar, b2x squared. Try that again. b2x squared plus b1x plus b naught. And then you can show that this sum in general is going to stay a second degree polynomial or less, regardless of a1, a2, or a naught, what they are. Those can be arbitrary. Okay, so this is yes. Yes, a subspace. So look at more of those cases. We will go over more in the problem sessions, in the study sessions. We'll go over more of those. Okay, next we will get on to more things. In 3.2, we're going to do linear combinations, spanning sets, linearly dependent and independent, bases. So we got a couple more videos to do still.